In the last video deriving the rotating atmospheric equations, on this line of the derivation, we use the fact that d(I hat dt is equal to omega cross I hat, dj hat dt is equal to omega cross j hat, and dk dt is equal to omega cross k hat. And in this video, we will be deriving those equalities. So to start with di dt, we can draw the Earth sphere like this. Just imagine this is spherical. I did the best I could drawing. We have that it's rotating around this way into the page. So that's what this is arrow showing, into the page. We have the distance at a specific point on the edge to the center line. We call that capital R. And then the line from the very center of the Earth to the atmosphere we call A. We could use R, but it's we don't want it to confuse with capital R. And then the latitude, which is phi, is this angle. So for example, if you're at 90 degrees latitude, you're up here. If you're at 0 degrees, you're here. And this would look like it's at 45 degrees. So now for the I direction, we want to look at I, which is into the page. So we look at this circle, which is now we're looking from a top-down view at this point. And so now, instead of being into the page, I is going up on the page. And so we have I1's here, and then I2 is here. So after a certain amount of time, we have delta I. We have I2, which is this vector, is equal to I1 plus some change in I. Because in the rotating version, we're saying that the I, j, and k components are changing in time. And then this will be delta I, which is equal to I2 minus I1, which if you subtract I1 plus delta I minus I1, you'll get delta I. And the reason why this direction is I2 minus I1 is because if you have a vector situation like this, we have A here and a vector B here, then this will be A minus B. So one thing we can tell from this situation is using the arc length formula, we can see that the amount of the angle, we're calling it d lambda, because this angle here will be lambda, which is the longitude. D lambda times this side, so I1 will be equal to this side. So the angle this side, and then we get this side, is d lambda. And since the magnitude of a unit vector is always 1, then we have that the magnitude of di is equal to the magnitude of delta I is equal to the magnitude of delta lambda. And this we will use later. The next thing we can do, which we also need for later, is to show that delta lambda delta t is equal to omega. So we start with the fact that delta lambda is equal to the distance away from the center over the total distance r. And We also know that distance is equal to velocity times change in time, because velocity equals distance over time. So we can multiply that over and get that distance equals v delta t. And now we can plug that in here. We get delta lambda equals v delta t over r. And we also know by definition that velocity is equal to the speed of rotation in radians per second is times the distance from the center. So if you're at the center, the rotation is the velocity of a particle would be nothing. But if you're at the very edge of the atmosphere, it would be equal to omega times r. So basically, you can say that velocity scales by distance from the spinning axis, which is spinning at the rate omega radians per second. So now we can plug this in here. We get delta lambda equals omega r delta t over r. The r's cross out, and we're left with omega delta t. We divide delta t on both sides, and we get delta lambda delta t is equal to omega, the rate that the axis is spinning in radians per second. Great. Another thing that we will need to know is that the vector for that rotation, omega vector, is equal to its magnitude, omega, times its direction, which is cosine phi in the y direction or j direction, plus sine phi in the k direction. And I'm not 100% sure that this is the right way of thinking about this, but I'm just assuming that we draw a triangle here, and this latitude will show up here in this location as latitude. Then we can use, we know that this is the j direction, this is the k direction. So by trigonometry, the adjacent side of the angle phi we can write as the length or the vector times the angle, so the cosine of the angle. So if cosine phi j, then here it's also in the positive k direction, and it would be the opposite angle, so it's sine k hat. And we know it's for a vector, it is equal to its magnitude times its direction. And so you have cosine phi j plus sine phi k. And so now we know this. And now we also need to figure out one more thing. So let me think. We also need the direction of the r unit vector, which is the unit vector for this direction r, because this can be pointing many different directions. So to find the unit vector, we can extend out a triangle here, and we know from geometry that this latitude, this phi, will be here, and we know that this is the adjacent side, this is the longest side, the hypotenuse, and this is the opposite side. So we can get adjacent side is cosine k hat, and this side is pointing in the negative j direction because j is this way, which I can write. Well, here, we were already here. It's negative j. And then this side we can reflect to this side, and we know it's a negative j, it's the opposite, so it's negative sine phi j. So now we have another thing we need to know, which is r hat is equal to negative sine phi j plus cosine phi k hat. And now to write delta I, we know its magnitude times its direction, as in for any vector. And we know from up here that its magnitude is equal to the magnitude of delta lambda. And we know that, as we can see in this case, I1, and we have delta I, it's hard to see because this is an oval, but it should really be a circle, that this vector will always point, this delta I will always point in the direction of negative r hat. So we take the negative of this, we'll get positive sine phi j minus cos phi k, and then we have the delta lambda here. Now we can move the delta lambda to this side. We get delta I delta lambda is equal to sine phi j minus cos phi k. And we can take the limit as delta lambda goes to 0, so making it infinitesimally small distance between one angle and the next angle. And this will give us partial I partial lambda is equal to sine phi j minus cos phi k. Next, we can write delta I as using the rule in calculus, which is, you can turn this into this type of form. You can just remember it's delta I delta lambda, partial I partial lambda delta lambda plus partial I partial, I believe this is phi. Let me write that. Phi. Partial I partial phi delta phi plus partial I partial z delta z. And since this is a solid body rotation, which basically means that as the Earth rotates, every part of it is pretty much rotating exactly the same amount, the same way. It's not like one part's rotating, one part's not. And this is obviously correct. I don't believe there's any situation where it wouldn't be. In that situation, these terms go to 0. There is no change in delta z or delta phi. So we're left with just this part. And we can divide by delta t, divide by delta t. We get delta I delta t is equal to partial I partial lambda and delta lambda delta t. And now we can take the limit as delta t goes to 0 as the time step gets smaller and smaller, and we get di dt is equal to delta I delta lambda. Well, in addition to doing that, we can also we do two things in one step. So this goes to 0, but additionally we also have that partial lambda partial t is equal to omega. So this will lead us to the step here. Let me see. Yeah, this was one that I'd start earlier. And we also made this change. So we get di dt is equal to omega times delta I delta lambda. And we showed just a little bit ago that that partial I partial lambda is equal to sine phi j minus cos phi k. And so we can write this as omega times the quantity sine phi j minus cos phi k. And if you know the rule for the curl notation, this is actually exactly equal to omega cross I. Knowing that omega is equal to omega cos phi j plus sine phi k. Therefore, we have that di dt is equal to omega cross I. And just to expand on what I was just saying, when you take the cross of two things, we have omega cos phi j plus sine phi k. We cross this with I. It will be plus 1I plus 0j plus 0k. We get, it's in this form. It's, you can take out this part, so it's the magnitude times the determinant, and you always put I, j, k up here. Then you put the I component, which is 0, then cos phi, j component, and then sine phi, k component, and then we put, this goes with the I, so it's 1, 0, 0. So that's that. That's how we would write the cross. So that was just showing how to go from this direction to this direction. But now I want to show how to get here to show that this is indeed equivalent to this. So we have this term. So, okay. So what we do is we first look at I, or you can write like this, plus, minus, plus. We first look at I, so we do this, and therefore we're looking at the determinant of this, which is cosine times 0 minus 0 times sine, which is 0. So there's no I component. Now looking at j, we have 0 times 0 minus 1 times sine times negative j, because it's negative. So we have negative j times negative sine phi. And then for k, we have positive k times 0 minus cosine phi, so it's minus k cosine phi. And as you see, this part is sine phi j minus cos phi k. Well, what do you know? That is exactly what is written here. So therefore we've proven that. Now for the next part, we're going to look at the next two derivations that we'll need, which is dj hat dt times dk hat dt. Now for this, we're going to do a slightly different derivation that looks something like this. As you notice, this is not looking like that, and there is a way to do it in this way, but I think it's there's a few steps in that are a bit counterintuitive, so I have the habit of writing it in a different way when doing j and k. So now we can look at a different view of the Earth, where we have the radius a, we have r is here now, this is phi, and then this rotate this angle in the I direction, which is d lambda, which is longitude, is here. We also have delta x here because this is the x direction, and we have j going this way. And so we do a similar kind of thing. We have j1 here. Apologize. These are supposed to be j's. Then we have j2 here, and we have delta j here pointing this direction. And I'm not 100% sure why that direction is the negative I direction. If anyone knows, they can say in the comments. At this point in time, I'm not sure. I kind of just memorized this, so hopefully I'll know in the future. So we can start with dj dt is equal to the limit as delta t goes to 0 of delta j delta t. And we can then write, because for a vector, because this is a unit vector, delta j hat is also a unit vector, is equal to its magnitude times its direction. So we know its magnitude is, the magnitude of this part is just putting the magnitude around it, because we don't actually know what the magnitude is. and then at the yet, and then the direction -I. So that's what goes here. So we're going to use something called the similarity of triangles rule. So it's like a proportionality between triangles of different sizes that the proportions should still stay the same. So we have this upper part, dj, over the magnitude of this, over the magnitude of dj, which is actually would be dj1. This is referring to dj1. So you have this over this, and then that will be equal to this part, because you can see they're kind of the same direction, divided by this part. So here we had this over this, now we have this over this. So we can, and we also know that the magnitude of j is actually just equal to 1 because it's a unit vector. So we get dx over a over tangent phi. Now why is this side called a over tangent phi is you can look at it like this. We have this side is here, this side is here, and then we can write it all the way down. We have a. So this is adjacent, this is opposite, this is the hypotenuse. So you can write that this side length is a over tangent phi. There's a rule in geometry or in trigonometry for that. So we can multiply by tangent phi over a by tangent phi over a. This part will go to 1, so we'll get delta x over a times tangent phi, which is just equal, tangent phi is sine phi over cos phi. And now we need to deal with this delta x over a term. So we know that delta x over delta t is equal to u, the x velocity. We use u for x velocity. And there is a rule dealing with spherical coordinates that is saying that delta x delta t is equal to the radius times cosine phi times delta phi d lambda over dt. So I won't be deriving this because I'm not sure actually how to derive it. This is another thing I memorized. We can then divide a on both sides, so we'll get delta x over a is equal to cos phi and then d phi. And the actually this will be a delta as well. Right, that'll be delta. And the t's just go away because you can multiply on both sides by delta t. So, and we also divided by a, so we'll have this. So now we know that magnitude of delta j is equal to dx over a, which is cosine phi over delta lambda. And then when we multiply this here, the cosines cancel out, and we're left with sine phi delta lambda. So now we have that dj dt is equal to the limit of this term, and we know now that this, see here, or what we have here, is the sine phi delta lambda. The delta t is still here, the negative I is still here, and this we know is equal to omega. So we have negative omega sine phi I. And similarly as before, we can show that this is equal to omega vector cross j. So I'll just show that for a second. So to write omega cross j, it is equal to omega I j k 0 cos phi sine phi 0 1 0. So if you see for j, it's 0 times 0 0 times sine, so that's 0. And for k, it's a 0, 0, and a 0 in each multiplication, so it's 0. So the only thing that's left over is the I part, which is I times negative sine phi. And as you see, that's exactly what this is. And we forgot this part, so there's also a phi here. So you see that's exactly the same. So finally, for the k direction, we can draw a circle like this where we have a going all the way up here. Delta x will be going kind of, yeah, right, because, yeah, this is the x direction. So we have k, we have k plus delta k, which can also be reflected out here because they're parallel with each other. And then this direction is delta k. So we have dk dt is equal to limit as delta t goes to 0 of delta k delta t, which is equal to the limit as delta t goes to 0 of the magnitude of delta k times I. And again, I'm not sure why it's the I direction. Well, yeah, I mean, I'm assuming that this is in the I direction. I just don't really have a clear visualization of that. So again, using similarity of triangles, we have this side delta k over k is equal to the longer one, the longer one over a. Delta k is here. I'm not exactly sure for this similarity of triangles, but it is supposed to be a similarity of triangle situation. So it's this, and remember, magnitude of k hat is 1, so we have that this is equal to delta x over a. And we just proved here that delta x over a was cosine phi d delta lambda. So here we go. And plugging that in here, we get limit as delta t goes to 0 of cosine phi delta lambda delta t times the I direction. This is equal to omega. So we have that is equal to omega cosine I. And we can show that is equal to omega vector cross k hat. And just to show that, we have that omega cross k hat is equal to I j k. This part gives us, the left part, the omega vector gives us 0 cosine phi sine phi, and the k, because it's 0i plus 0j plus 1k is 0, 0, 1. If we look at I, we will get something. But if we look at j, it's a 0, 0, 0 in this multiplication, 0 in this multiplication, so that's 0. Same here, 0, 0, 0. So using the I, it's just I times the determinant of this part, which is equal to I times cosine phi. Well, what do you know? That's exactly what we have written here. And again, I forgot that there is a omega here. So again, that's exactly equal to this. So therefore, we proved that these two are equal. And if you're wondering, is there a way to get from here to here in this direction? Not really. It's kind of just this direction because we have a nice notation for this. So how did they know that this was the case? They probably did a lot of trial and error and realized that it was equal to this. And once they know that, they're like, oh, that's a pretty easy pattern to remember. So therefore, we've shown that. And one thing to mention is we've assumed in this case that to get the derivation working for a rotating body, we've assumed that these are, a function of time. I, j, and k. But I mentioned previously that that will give us a Coriolis force because of the rotation. But the Coriolis force in that case is not complete because there is curvature to the Earth. So it turns out that, for example, I is not just a function of time, it's also a function of space. It's also a function of x. And j will be a function of time and y. K will be a function of t and z. In this case, we just assumed this. So that's why we got to our result. But in reality, we'll need to look at the terms that deal with x at space as well, because I, j, and k are also dependent on space. The unit vectors are dependent on space. So in the next video, in the atmospheric dynamics series, I will include this part. And now we don't need to actually redo anything because we can keep the part we just did now as one part, and we can focus on the space part and then put the two back together. So if you're interested in that, stay tuned for the next video. Thank you.